All right, hi guys. We're going to work on the last topic, which is alpha, beta, and gamma decay to finish up our unit on modern physics and finish up the year. So our first type of decay is alpha decay, which is the least penetrating of the nuclear decays. And the Greek letter alpha, which is the little fish symbol, is used to show this type of nuclear decay. So basically, you start out with the isotope of the atom you're given. So remember that an isotope is an atom that has a different mass number. So the number of protons are the same, but it might have more neutrons. Okay, so we have bismuth here, and this is bismuth 211. So this is the mass number, or the atomic mass, 211. 83 is its atomic number, which is the number of protons it has. Okay, so when it decays to give an alpha particle is basically a helium atom. And a helium atom has mass number 4, atomic number 2. Okay, so that is your alpha particle. Because of conservation of mass, conservation of charge, all those conservation laws, we have to have the same number of total your mass number and the same number total your atomic number on one side of the equation as we had to begin with our bismuth atom. So since we have 2 here that went to the helium, that means you still have to have another 81 to add up to 83. So our other atom, which is called the daughter atom, and this would be the parent, is 81, atomic number 81. Mass number would be 211 minus 4, or 207. So 81, we go to the periodic table, and that is thallium, Tl. And so you have one atom, the parent atom, bismuth, by giving off an alpha particle, in other words, a helium atom, transformed or transmutated, the term is transmutated, into a different daughter atom, namely thallium, with 207 mass number and 81 atomic number. So that's an alpha decay. Let's try another one. Let's say we have plutonium. Plutonium, by the way, is out of all the elements, the most radioactive element. So its atomic number is 94, which means it has 94 protons, and its mass number is 236. So you see that you have a lot more neutrons than you do protons, which is why it's unstable. Okay, so it's going to give off an alpha particle because we said it's an alpha decay. So again, the alpha particle is the helium atom, 4 and 2. So we're going to take 94 minus 2, that gives us 92. And 236 minus 4, which gives us 232. And 92, I'm pretty sure, is uranium. It is. So your plutonium transmutated into uranium by giving off an alpha particle. And so that is alpha decay in a nutshell. Our second type of decay is beta decay. Beta decay is not as common as alpha decay. It's a little bit more penetrating. Where alpha decay can be stopped by a sheet of paper, beta decay needs a sheet of aluminum foil, basically, to stop it. So it's a little bit more penetrating. And what it does, at least the one we're going to look at what's called negative beta decay, is that it gives off a negative particle, an electron, and something called a neutrino. The neutrino is just a little particle that accounts for the difference in mass. It doesn't have a charge of its own. Okay, so we're not going to worry about the neutrino. We're just going to look at the electron that's being given off. All right, so we start out with the isotope of cobalt. And cobalt is going to give off a beta particle. And a beta particle is essentially an electron. So it's -1, 0, and that's an electron. That's what we call our beta particle. Okay? Which means that our atomic number, we're subtracting 1. So we have to go up by 1 in order to still end up with 27 for our atomic number. So our new atom is going to have an atomic number of 28. The mass number did not change. It's still going to be 60. So we look at the periodic table and find number 28, which happens to be nickel. And so once again, we have what's called a transmutation. We started out with cobalt as the parent atom. We gave off an electron in beta decay. And because of that, we transmutated and formed a daughter atom, which is nickel. And its atomic number is 28. So in other words, beta decay is going to make your atomic number increase by 1. It's going to go up by 1. Okay? Let's try another one. We're starting out with lithium. So lithium is atomic number 3, mass number 8. Okay? Again, we're giving off a beta particle, an electron. So our atomic number is going to go up by 1, so it's going to be 4 now. The mass number will stay the same, so it's 8. Atom number 4 is beryllium. So lithium gave off a beta particle, an electron, and became beryllium. So again, it transmutated. These are all examples of transmutation. Okay? Now let's look at our last one. Gamma decay. Gamma decay is the most penetrating. That will go right through you. It'll go through your entire body. It can only be stopped by about 6 inches of lead. Okay? So it takes quite a bit to stop it. It's very penetrating. This is the most dangerous one. So we start out with radon. No, radium. Sorry, I always get confused those two. So we start out with radium, which has a mass number of 222 and an atomic number of 86. And we're going through alpha decay first. Because what gamma decay does is it goes through one of the previous types of decay, alpha or beta, but it doesn't go down to its ground state. It's still unstable. And so it has to give off a gamma particle, which is basically a photon of light, which is very, very high energy. So it gives that off, and then it comes down to its ground state. So we start out with radon. Radium. Yeah, radon is Rn, radium. So we start out with radium, and we are going to alpha decay it. So we have Ra, 86, 222, yields a helium atom. And 86 minus 2 is 84. 222 minus 4 is 218. And our new atom with an atomic number of 84 is polonium. Okay? But it's still excited. So we're going to use a little asterisk to show that it's still not in its ground state. It's still excited. So what does it do to go to its ground state? We start out with this atom, 218, 84, polonium, and its excited state. It gives off a gamma particle, and the gamma particle is this, okay? That is a gamma particle. Plus, it's still going to be 84, still going to be 218, still going to be polonium, but now it came down to its ground state, so we don't put the asterisk by it. A gamma particle is basically a photon of light, a light particle. Okay? So that here is what shows gamma. You have to go through one of the other decays prior to going into gamma. All right, let's do a second example. Let's look at beta decay. 13153 iodine. We're starting out with iodine, and it's going to go through beta decay first and then gamma. So 13153 is going to beta decay, which means it's going to give off an electron. So its atomic number is going to go up by 1. Mass number stays the same. Its atomic number is 54 now. So 54 is xenon. Xenon. And it's still excited. So we want to get it to its ground state. So our next step is that the xenon, which is excited, that's what the asterisk means, is going to give off that gamma particle, the photon, and come down to its ground state. And that is denoted in that manner with a gamma particle being given off, and then you remove the asterisk from the xenon. And that's it. So you've seen the examples of alpha, beta, and gamma decay, and how to balance the equations. That's the last thing we had to do to complete the year. So I'm going to post the assignment on EDSB with a periodic table, so you don't have to go in search of one. So please complete it for homework. It's due on Wednesday. All right? Thanks. Bye.